This is section 5.1. It's the normal distribution. And the reason it's the most important is because it is very common. We see it all the times in nature. So anytime where you have like the heights of people or weights of people, like tree diameters, scores on tests, repeated measurements in a lab experiment, like lengths of anything, most of these things end up being normally distributed, or at least close to normally distributed. Okay, so it's probably the most common distribution we will ever use, and it's very important in all of our statistical procedures that we do for the rest of the semester. Every other distribution we're going to use will be based on the normal distribution somehow. The assumptions for almost all of our tests we'll do, all of our procedures will almost always be that it is a normal distribution. The normal distribution is symmetric and bell-shaped. It's also called the Gaussian. It's the bell curve. When you've had teachers say, I'll grade you according to the curve, this is what the true curve was supposed to be. Okay? So if they said, I'm going to curve your grades, that means they make your grades look like this, which really means that only a few people would get high scores, a few people get really low scores, and a lot of people would get like C's and B's. So usually when people curve your grades, like if I curve your grades, I will just shift everyone's grades up, but that's not a true curve. You don't actually really want your teachers to curve your grades. The PDF for it is this formula. So f of x equals 1 over sigma square root of 2 pi e to the negative x minus mu squared divided by 2 sigma squared. Okay. It's a fairly complicated looking PDF. It is in fact so complicated it is impossible to integrate and get a closed form. You have to use your more analytic techniques or computers to actually find these areas under a curve, which means throughout this class, if you want to find any probabilities for the normal distribution, you have to either use a computer or use a table. We can't find the CDF in the closed form. Okay, and it is defined for all possible x values from negative infinity to infinity. Okay. The expected value of x is the mean mu. The variance is sigma squared. So the standard deviation is just sigma. Okay. And we're going to use the notation x is distributed normally with a mu and sigma squared. So that's how we write it. And we also a lot of times say that x is normally distributed. So we'll say x has a normal distribution, or x is normal, or x is normally distributed. So we're going to explore this applet, hopefully. Okay. And notice for this applet that I can change the mean and the standard deviation. So we're going to explore with changing the mean first. So the mean is my top slider. Notice what happens to the graph when I change the mean. So if I make the mean lower, what happens to my graph? It shifts to the left. If I make my mean higher, so I'm making my mean higher, what happens to the graph? It shifts to the right. Okay. So what does changing the mean do to the distribution? If the mean goes down, we shift to the left. Okay. If the mean increases, we shift to the right. So changing the mean, all it does is just slide your curve up or down. What about the standard deviation? So standard deviation is my second bar here. So I'm going to make my standard deviation get smaller first. Okay, so as my standard deviation gets smaller and smaller, what happens to my graph? It gets taller and skinnier. Okay, more narrow. I'm going to make my standard deviation bigger now. What happens to it? It gets fatter and more spread out. So if the standard deviation increases, the graph gets fatter or more spread out. And as the standard deviation decreases, the graph is narrower. And just to remind you of this, we have these two pictures from the book. So in this second picture, notice what's the only thing that changed? They changed the mean. So when they changed the mean, it shifted the graph. Okay, in the first picture, they kept the mean the same, so they're centered at the same place, but they changed the standard deviation. So the shorter, fatter one has the variance of 4. The tall, skinny one has the variance of 0.25, so that's a smaller variance. The first thing that I like to learn about the normal distribution is the empirical rule. And this is the first time that we really get a direct application of the standard deviation. So in a normal distribution with a mean mu and a standard deviation sigma, we've learned from experience that, I mean, you can figure it out too, but in the normal distribution, the middle 68% of the observations, so that when I say middle, I mean the observations around the mean. Okay, so the 68% of the observations in the middle fall within 1 standard deviation of the mean. If you go out to within 2 standard deviations of the mean, so from here to here, that's going to contain 95% of your observations. And if you go out to 99.7%, you're going, or 3 standard deviations, if you go out to 3 standard deviations, you will contain 99.7% of your data. So, for example, the distribution of heights of young women is approximately normal with a mean of 64.5 inches and a standard deviation of 2.5 inches. So what does our empirical rule, or the 68, 95, 99.7 rule, say about this distribution? Well, to start with, we know that the distribution will always be centered at our mean. So the center of the distribution has to be at the 64.5. Now, if I want to go out 1 standard deviation, what will my numbers be? So 64.5 plus or minus 1 standard deviation is going to go from 62 to 67, right? So from here to here, how much of the observation should fall between those two bounds? Okay. So we have then 68% of heights are between 62 and 67 inches. Now let's try 64.5 plus or minus 2. Standard deviations. So 59.5 to 69.5. So that is everything in between those two numbers. It does include the middle as well. And that will tell me that 95% of heights are between 59.5 and 69.5. And if we go out even one more, 64.5 plus or minus 3 standard deviations, it's from, let's see, it goes from 57 to 72. So 97% are between 57 and 72 inches. So from here to here.
How are you getting the 97%?
Oh, 99.7. 99.7%. Okay, notice that does include everything so far. So within the 3 standard deviations, I will contain almost all of my data. 2 standard deviations gives me 95%, 1 standard deviation gives me 68% of the data. And that's what I can do with the empirical rule. Other questions with it? So we can say things like 10th graders in Indiana took the English exam. The mean score is 572, the standard deviation was 51. The scores were approximately normal. What range of scores includes the middle 95% of the scores? So we want to find the 95% of the scores. How many standard deviations should I be away from the mean then? 2 standard deviations. So that's going to be basically the mean plus or minus 2 standard deviations. So my mean is 572 plus or minus 2 times the standard deviation of 51. So 470 to 674. So the middle 95% of the scores range from 470 to 674. So that's pretty simple. So then the next thing we want to do is we say, okay, well, we use this rule to find the middle 95% of the scores. But what if we wanted to find, say, like the middle 90% of the scores, okay, or the top 10% of the scores? Okay. And so what if we wanted to do this for our normal distribution with a mean of 570 and, well, if I write it like this, we're supposed to write mean, variance, so I'm going to put the squared there because our standard deviation was 51. Now, because there are so many possible normal curves, it would be impossible to make a table of probabilities for all of them. Because remember we said we can't find the CEF, we have to use tables of probabilities. So what we're going to do is we have one table of probabilities for the what we call the standard normal curve. So in general, what we're going to do is we're going to standardize, so we find a z-score for any observation and any normal distribution. And the way that you standardize is we're going to do value minus mean of the value over standard deviation of the value. Now this is our general format that we will use for the rest of the course. Okay, and we'll change a little bit for each situation. But in our situation, if we have just a random variable x that's normally distributed with our mean mu and any standard deviation sigma, then you standardize with this formula. So it will be x minus the mean over the standard deviation. And our new random variable z has a standard normal distribution. So it's the standard normal distribution with a mean 0 and standard deviation 1. So let's try it out. So how would you standardize the normal distribution with a mean of 64.5? And remember we put the variance second, so variance equals 6.25, which means my standard deviation is the square root of 6.25. which equals 2.5. You do have to be careful with this notation because most books put the variance second, some books put the standard deviation second. And I am switching over. The last class I taught put the standard deviation second, so when I accidentally say standard deviation second, you can correct me. Okay. So if I want to standardize, basically what I have to do is I have to plug everything into this formula. It will be that z equals x minus my mean of 64.5 divided by the standard deviation of 2.5. And what our new random variable z tells us is you can also think of z as z is the number of standard deviations you are from the mean. So if you are at 64.5, how many standard deviations are you from the mean? You are 0 standard deviations from the mean. Okay. If you are at 67.67, you are how many standard deviations above the mean? You are, okay, so 64.5 plus 2.5 gets me to 67. So you are exactly 1 standard deviation above the mean, so z is going to be 1. So these are all the numbers we found in the previous example. 69.5 was 2 standard deviations above the mean. 72 is 3 standard deviations above the mean. Notice if you want to go to 62, you're 1 standard deviation below the mean, so we put z is negative 1. 59.5, z is negative 2. Okay, so let's do a specific value. Let's say for x equals my 59.5. If I want to find my specific z value, I'm going to do x minus my mean of 64.5 divided by my standard deviation. When you put it in your calculator, you are going to get negative 2 because you are 2 standard deviations below the mean. So for example, we want to standardize these following observations. So let's say that x equals 3 and it comes from a normal distribution with mean of 2, variance of 4. And if my variance is 4, my standard deviation is the square root of the variance, so square root of 4 gives me 2. So I guess that's slightly confusing because my mean and standard deviation will be the same thing. And x equals 3, so we start with our formula. This is a formula you should probably memorize. So it's x minus the mean over the standard deviation. So I plug in my 3 minus my mean of 2 divided by my standard deviation of 2 gives me 1/2 or 0.5. So this person that was a 3 is 0.5 standard deviations above the mean. So for my next one, a person gets a score of 273 on a test, so x equals 273, with a mean of 290 and a standard deviation of 16. Assume the test scores are normally distributed and we want to standardize our x value. So again, I just plug everything into my formula. So x is 273 minus my mean of 290 divided by my standard deviation of 16. Negative 1.0625. Okay. Notice that it's negative. We know that this person is negative about 1 standard deviations below the mean, so they did score below the mean.
So on the previous one, that 4 was the variance?
Was the variance. So our book will use the notation normal, mean, variance. Okay. So next time I teach that, I'll change that variance to like a 9 or something. Okay, on the test especially, I try to never use this notation. I try to actually say the mean of 2, the variance of 4, just so that you don't accidentally mess it up.
Wait, so in our homework thing was the second number with
The second number will be your variance. Yeah. And your book does use this notation a lot, so you need to be used to it. The second number will be your variance in this textbook. So go ahead on your own, try number 3 and 4. I'll write them up here and then we'll check and make sure we have the same answers. So for number 3, I got that Bill's z-score is negative 0.41. Now let me tell you a few of the most common things that or probably the most common mistake I see people make in this class, or well, in the lower classes when they do this, is they switch the x and the mean. So they do 10 minus 9.3. Okay, so that's probably the most common thing I see. The second most common thing is if I tell you a variance of sigma squared equals 3 and they forget to take the square root to get the standard deviation. Okay, so for number 4, I get 5.2. So this person or thing was 5.2 standard deviations above the mean. Okay. Now you'll notice that I tried to round these to 2 decimal places, and the reason why is that makes it easier to use your table that we're going to learn how to use. Okay. So if you're going to use a calculator computer, I'd probably still go out to 4 decimal places just for more accuracy, but as far as the actual table, you need to be able to use 2 decimal places. Now, to go through, let's learn a few more things about the standard normal distribution. We've already said them, or said a couple, but just to really make it clear. So the standard normal distribution has a mean of mu equals 0 and a variance of sigma squared equals 1, which means what is my standard deviation? My standard deviation is also 1. Now, so we say x is distributed normally, 0, 1. The PDF, we use this notation phi of x. So this is lowercase phi. This is uppercase phi. So lowercase phi, uppercase phi. So the PDF has a notation lowercase phi of x. Don't ask me why they made up a new symbol for it. And if we take the original PDF and plug in my zeros and ones, it simplifies just a little bit. So it's 1 over the square root of 2 pi e to the negative x squared over 2. The CDF has a notation, again, uppercase phi of x, and it's the CDF, well, we would define it as you'd have to integrate from negative infinity to x, and it'd be your PDF with a dummy variable, in this case, y. Now again, like I said before, you can't actually integrate this and get a closed form. Okay, you cannot integrate it, so we have to use a table or computer to find all of our probabilities. So these are just a couple pictures that are in your book that I wanted to make sure you looked at and you were familiar with. Okay. So these are again for the standard normal distribution. So this is a picture of the PDF. Notice the mean is centered at 0. And your book has this pi equals 0. I think what happened is a carryover from an old edition where they use pi's instead of mu's for their means. Okay. Some people use that notation, but it's the mean is 0, so it's centered at 0. I can't see it on here, but this is a sigma equals 1, so you can kind of see your standard deviation goes out this far, and the equation of the PDF. Now your CDF for your capital phi of x, the CDF is always defined as the area to the left of x. Here's a picture of the actual CDF itself. So this above was the PDF. This is the actual CDF. Notice it makes kind of a cool S-curve. Just kind of interesting to see once. And then there's this thing tells us something that we will use over and over and over again. Okay? So if you have a normal curve, it is symmetric. Okay? And the fact that it is symmetric means if the area in this tail, if the area to the left of negative x is, well, what the area is, then the area to the right of x will be the same thing. Okay? So the area in the tails is always going to be the same. So the area to the left of negative 3 is the same as the area to the right of positive 3. Now this next thing is what the actual table looks like in your book. At the back of your book, somewhere between the end of the chapters and I think it's before the solutions manual or before the index, you have a table. There's a couple tables. This is the standard normal table. So this is what it actually looks like. So it looks like this. And I blew up these two pictures so we could look at them. So for this picture, okay, it's there to remind you that the table always gives you the area to the left. So the table always gives you the area to the left. How would you find the area to the right of any number? You would have to use the complement rule and do a 1 minus. So this reminds you it always gives you the area to the left. And then this next picture is something that we'll talk about when we get to that point. Now to look at the actual table, okay, notice that there are the two columns on the, well, the column on the outside, the top row. Okay. These are your actual x values, and then on the inside is your probabilities. So notice that we can come down, and this is like x of a negative 3.4, and then this is 0.00, okay, or 3.4 and 0.01. What it is you come down the side to get your whole number, your first decimal place, and then you go over to the correct column to get your second decimal place. So if I want like x equals, or sorry, z, because this is a standard normal curve, if I want z equals 1.73, then I find 1.7 on my row, so these are all negative numbers. Flip the page, there are 2 pages. Flip the page and you get to 1.7, and then you go across to the 0.03, and where they intersect, that would be your probability to the left. So that's how the table works, and now we're going to try it out. So again, remember the table gives us the areas under the standard normal curve to the left of z. So for this one, if I want the probability that z is less than or equal to 2, I am looking for the area to the left of z equals 2. And that is convenient because my table will give me the area to the left of negative 2. Oh, it was positive 2, right? Need this to work maybe more. Okay. And like I said, I made the images and then I forgot to put them on here. Okay. So if I want the 2, I can show you on this graph, I need to go to 2.0, and then I need, what, for my hundredths place, I need the 0 again. So if you look at that, so 2.00, the area is 0.9772. So for my next example, now I want the probability that z is greater than or equal to 2. So here's my 2. Now I want the area to the right. Again, if I look up 2 on my graph, it will give me the area to the left. So the area to the left is 0.9772. So how do I find the area to the right? 1 minus 0.9772 gives me 0.0228. If any of you guys have your books, I would get them out and actually flip to this table in the back so you can follow along with us. And I do actually have a stack of normal tables that are from another class, so I'll give you the same answers, but a slightly different table that I can bring to class in the future as well so you can follow along. Okay, so now this time I want z is less than or equal to -2. So here's my -2. I want the area to the left. So to do this, I need to go back up to my table. Okay. And I'm looking for -2.0. And notice that gives me my 0.02. I can see it on my paper copy easier. 0.0228. So it's 0.0228. So what do you notice about this one and the previous problem? Okay. Well, the area to the right of +2 is the same thing as the area to the left of -2. Because it's symmetric, the area in the tails will always be the same. Okay. So let's go back up and look at the top one on the other side of the worksheet. So the probability that z is less than or equal to 3.18. So 3.18 would be somewhere about here, and I'm looking for everything to the left. Okay. What do you think that's going to be, or close? What is it going to be close to? Should be close to 1. Let's come up and look for it. We're looking for 3.18. So 3.1, I go down the side to my 3.1. Oops, we lost it all. Okay, so I want 3.18. So I go down the side to 3.1 and across to the 0.08. And that gives me 0.9993. The next one is kind of similar. We have the probability that z is less than or equal to 4.5. So my 4.5 would be over here. I'm looking for all the area to the left. What do you think this probability is going to be? It should be almost 1. Okay. Now if you look at your table, You'll notice your table, the z values only go up to 3.49. Okay, and so 4.5 is going to be somewhere way over here. So that probability is going to be very, very close to 1, even more so than 0.9998. And so I usually just say approximately 1. Okay, and that's going to be close enough for all of our intents and purposes. So this next one, okay, now we're going to throw something else into it. So now we want the probability that x is between 0 and 2. So here's my 0, here's my 2, and I'm looking for the area in between. Okay, so get creative. There are several different ways you could do this, but what do you want to do to try and find this area? Okay, subtract these two areas. So for example, the area, so we could do like the probability that z is less than or equal to 2. So that would be from 2 all the way over, and that was, look up above, what was it? Was it 9778? 9772? Okay. And then I can find the area from 0 to the left. So if you look up 0 on your chart, what are you going to get? Should be 0.5, because we know it's centered at the mean, and my mean is 0. And then, so I'm going to the probability that z is less than or equal to 2 minus the probability that z is less than or equal to 0. So 0.9772 minus 0.5, so 0.4772. So if you take the bigger area minus the smaller area, you do get the area in between. Now, again, what would happen if you just accidentally change the order in which you subtracted them? You get a negative, which would automatically tell you that you did something wrong, because we can have negative probabilities. Okay. Now this concept is usually really hard for the statistics 2,000 people to get, but you're really used to saying if I want the probability that x is between two numbers, you're used to subtracting your CDFs. So this should be an intuitive concept for you, hopefully. Okay. So this next one, I want the probability that z is less than negative 2, so less than negative 2, or z is greater than or equal to 2. Okay, what do you think we should do with that? Find each of the probabilities and then do what with them? Add them together? Okay, so if I look at my negative 2, I get 0.0228. And if the area to the left of negative 2 is 0.0228, then the area to the right of positive 2 has to be 0.0228. So I can just add those together. .0456. For my next problem, I want the probability that z is between negative 1.32 and 2.45. Okay. Again, what do I need to do? Subtract those two probabilities. So it's the probability that x, sorry, I keep writing x's, don't I? These are z's. Z is less than or equal to 2.45 minus the probability that z is less than or equal to negative 1.32. Okay. Now technically these are both z is less than or equal to, these are CDFs, so you could get in the habit of using the book's notation, since that's what the solutions manual will be. So it's capital Phi of 2.45 minus capital Phi of negative 1.32. So if you have your book, go ahead and look at these two numbers. So if I look at my 2.45, I get 0.9929 minus, and look at my negative 1.32, I get 0.0934. 89.95%. Or my probability is 0.8995.
Question.
Okay.
It doesn't include bound if it's just not standards of the rest. Does that change probability a little bit?
Nope. Just the same thing. Anytime you have a continuous distribution, the probability at a single point is considered 0. So it doesn't really matter if I include that 1.25 or not. I'm going to skip down to the z is less than negative 6.39. Okay. So here's my negative 6 somewhere out here. And I'm looking for the area to the left. Okay. So what do you think that's going to be? About 0. Okay. Again, if you look up at your chart only goes to negative 3.49. So it's not even on your chart. And so it's off the chart. So again, I'm just going to say approximately 0. And then this one, the probability that z is less than negative 1.72 or z is greater than 0.63. No, that's not it, is it? It's z is less than negative 1.72 or z is greater than 0.63. Okay. So in this one we are going to have to get a little bit more creative. So, because what happens if I look up my negative 1.72 on my chart, that will tell me the area to the left. So if I look up negative 1.72, it tells me that the area to the left is 0.0427. But what will happen when I look up the number 0.63 on my chart? It'll give me the area to the left, and I want the area to the right. So I'm going to have to use the complement rule. So 1 minus, now I look at my 0.63, and I get 0.7357. Okay, but that was the area to the left, so I use the complement rule, subtract it from 1. 0.2643. Now, so that's the area in each one of the tails, and to get the total area, I need to add them together. .307. Now, when I go through and I work with all of these normal distributions and everything else, when we do confidence intervals and everything else for the rest of the semester, I really like to draw pictures. You'll notice on most of my problems I will draw pictures because it really helps me figure out what I'm trying to find, and I suggest that you try and get in that habit as well.